Okay, so the forward and the reverse voltage cancel each other out. There's not many people watching the recordings anyways. And you get this built-in potential across the diode, what we can calculate with VT, ln, KT, VT, ln, NA, ND over NI squared. If I put a reverse voltage across the diode, so I'm putting the positive voltage on the N side, I'm putting the negative voltage on the P side, the barrier height gets higher, and since VD is a negative number, V0 minus VD is a larger number. I increase the barrier height in reverse bias. And when I increase the barrier height, I'm going to decrease the drift current, the current due to voltage, whereas the diffusion current stays constant. So I get a smaller current overall. I actually get my current, if I look at my IV curves, IV for a diode, I'm going to exaggerate this a little bit. This is, I get a negative current in reverse bias because it's dominated by that diffusion current. When I go into forward bias, I now have a huge drift current, and it's going in the opposite direction of the diffusion current. So now I get a positive current that's basically dominated by drift current. And the net effect is I actually lower the barrier height by whatever V0 is, whatever V diode is. If I get to the point where the voltage across the diode equals V0, you achieve like a flat band thing where you get a flat voltage across the whole thing. Current can flow freely, like it's a short circuit. Many, many ways to describe how a diode works. Okay. Why are diodes so important? They show up in a couple of little circuits that you use. They're protection diode, ESD protection diodes. They show up in power circuits. They show up in power conversion circuits. They're not really a big deal when you're talking about processors or logic or things like that until we get into studying MOSFETs. And there's diodes all over the place that you don't even see. And a lot of the non-idealities of MOSFETs are based on the fact that there's all these p-n junctions in there. But they're actually pretty straightforward. Don't worry. I'm not going to do physics again in here. This is pretty much it. If I apply a voltage, this formula stays the same. The depletion width is going to increase in reverse bias. It's going to decrease in forward bias. That's my sanity check to see if I got the polarity right on my VD. Is to double check that. And you'll never have to take the square root of a negative number here. Because if you make VD bigger than V0, you're going to burn your diode out. You're in the region where it doesn't matter. The part that changes on the charge in the junction is this part again. Instead of having just V0 there, we have V0 minus the forward voltage on the diode. And Cedra may have it written in some places like that, and it may have it written in some places like this. And you may see those if you check on the internet too. It's the same equation. You should see the saturation current for a I think shut up. So it says we want to derive this, but we don't really derive this in here. Deriving it is a topic for the modular series on on solid state electronics. It's a great book. These were written by partially by a guy from Purdue and partially from a guy at ASU. But when we're thinking about this IS right here is really, it's representative of the diffusion current. Because when I put it in reverse bias, this term goes to 0 and I get negative IS. It's a characteristic of a diode. If you go to a diode data sheet, they will have IS on there. If you're the guys building the diode, you have to think about what influences IS and come up with ways to minimize it as you need to. And then it gets exponentially larger when I get into forward bias. Okay. In forward bias, the barrier gets lowered by the applied voltage. We've talked about this. And it's like opening up a floodgate that allows that exponential increase in current. Many carriers diffuse across the junction. We get this thing called minority carrier injection. And if you're someone who studies a lot of semiconductor physics, they'll talk about minority carriers. And what they are is, not this again. Great. I just changed the battery. I thought that would solve all my woes. Change to orange. Okay, I'm going to use my fingers. I'm going to give up for a moment. Minority carriers are N-type carriers in the P region and are P-type carriers in the N region. They still exist. They're still there. They're still an important contribution to the current. There's just not quite as many of them, and that's why they're minorities. Just not as many of them are out there. And the excess carrier, so the electrons in the P region are going to very quickly, within the terms of a couple of nanometers or so, find a hole because there's an excess of holes and recombine with them. They get absorbed rather quickly. They're there. When we get to bipolar transistors, there's a lot more of them in there. And a lot of these slides go quick. Okay. In forward bias, the excess concentration of, yay, it works. The excess concentration of minority carriers, this is on the N side, my P's, tend to concentrate pretty close to that depletion region. And as we get away from that depletion region, many of these carriers have found a site to recombine with. The P's have recombined with an electron, and they start going away. And this almost looks like it's an exponential curve, and it looks like a time constant, but it's really like a distance constant away from this, that it's decaying exponentially. The amount of time, the amount of distance it takes to get down to 1% of minority carriers is about 5 LP. It's called the diffusion length. And it follows the same mathematics as a time constant. And the diffusion constant, oh gosh, okay. So The diffusion constant is like how, okay, L is how long it takes it to. The diffusion constant is how likely it is. So the two together help form this part of the equation right here. And the physics behind that, again, is in this book. And we're not going to go into it in much depth in the class. But you can calculate IS. You can calculate IS using that part of the equation, if you know all those numbers. A little bit advanced for 280. I'm sure you could plug the numbers in. I don't ask you to do that on the homework. This is something that diode designers use. And if you go to work for somebody like TSMC, who's hiring 300 new grads this year, or Intel or Microchip, they have, you'll have to buy these books. They will help you get started. Yeah, there's been a lot of science behind this recently. Actually, even just not just setting your goals, but maybe writing them down. They found people who actually just write down their goals once a day are much more likely to achieve those goals. And because you're thinking more long term, it puts it in your head, this is what I'm going to do. And then you start finding opportunities and ways to do it. Like suddenly I have a single photon detector. The project's all mine. Oh, I really wanted to do that, but I didn't want to step on Vince's toes, but Vince doesn't want it anymore. So it's mine. Where does the junction store charge? It stores it in the depletion region, right in this area right here. And the amount of charge changes with bias. Now, typically the way we've thought about capacitance in the past is capacitors are linear and they're perfect. I have a whole day on capacitors and why they're not perfect in EE280 in the fall. Real engineers can talk about capacitors for days. If I divide that out, I get C equals Q over V. But the fact that this capacitance changes with voltage means it's a nonlinear capacitor. So I have to go to the more general form of this expression, where instead of saying Q over V, because Q and V aren't constants, it's the rate of change of charge with respect to voltage. And it can change, and that can change with voltage. It's a nonlinear capacitor. There are two types of capacitance here. We have the junction capacitance, which is pretty easy to see here. We've got charge separated by a distance. It's like the two plates of a capacitor, where really that's all that really matters. This is the more important capacitance, oh great, at reverse bias. Let's just, okay. At reverse bias. The diffusion capacitance dominates at forward bias. Not used very often. It's a smaller capacitance. We take it into account in our models, but we don't really worry about, we don't make useful devices out of that. We talked about varactors. These are the equations for, whatchamacallit, for junction capacitance. Big, long equations. We've talked about the subtleties of these. Make sure everything's in centimeters is the hard part. We've done a few of these. I could take this whole part right here and call it alpha to simplify my calculations. And I've already done a little bit of that in here too. This is the charge at the junction. If I want to calculate the capacitance, I have to take the derivative of this with respect to VD, which comes out to be, if you like calculus, you can do it yourself. Alpha over 2 times the square root of V0 minus VD. And this is we call this term at the top the alpha over 2, and then we normalize that CJ0. And CJ0 is just the zero bias junction capacitance, and it can be calculated like this. I don't even think I put this on the homework, and I certainly will not put this on the exam because I don't want to grade it. The diffusion capacitance depends upon, this tau here is like a time constant. It's how long in time as these carriers are moving does it take for them to decay away. And if we look at this equation, we could cancel IP out, and we say tau p is basically those two constants squared. The LP squared, over DP squared. It's just an equation. And again, that's not really all that important at this level, but just so you have an idea that these are derived and they do come from somewhere. Okay, this is good. This is what I need to spend more time on. Okay, chemistry. You learn about S and P orbitals. And those S and P orbitals are perfectly calculated for atoms in free space. There are no atoms in free space. You have to create a really high vacuum, and there's still other atoms around it. So what happens if you take a silicon atom and you start moving it closer and closer to other silicon atoms? These S and P orbitals start to kind of blend together and make sp orbitals. And then you get down to the point where you've got them in a silicon crystalline lattice, and it looks like this. I don't have to worry about the other parts of the diagram. I know in my semiconductor, all the silicon atoms are going to be at lattice spacing. So I abbreviate this whole drawing right here and make it look like this. I've got, this is called the valence band. And the valence band in silicon is pretty much all filled. At 0 Kelvin, it's completely filled. And I have the conduction band, which are the electrons that can move about the crystal easily, and they're mostly empty. I can put energy into here as long as the energy is greater of my particles, greater than the band gap energy. And I can do it by putting thermal energy in, heat. I can do it by putting electrical energy in, stimulating it with voltage. And I can do it by putting light in for like solar cells or for LED. Well, LEDs are backwards, but I could put a solar cell in here and it excite some of these electrons up here to conduct into the conduction band. An even more simpler version of this is what I usually draw when I'm talking about physics, is I just draw a line and say, okay, this is the valence band. All the states below that are filled. This is the conduction band. Most of the states above that are empty. This is the energy band model. Stuff I wish I knew when I started grad school. So basically what's going on here is at VA equals 0, diffusion currents moving this away and drift currents moving this away. The barrier height is such that all of these electrons here get turned away by the barrier height, and the drift current and the diffusion current exactly balance out and cancel each other out. If I put a forward bias, this slope is going to get less steep. So in forward bias, I still have the same amount of diffusion current, but the number of electrons that can make it across the barrier has gotten to be much higher, and now my drift current is higher than my diffusion current. Put it in reverse bias, now it gets way steeper. My diffusion current's still going on. All of the electrons that are stimulated by the electric field, by the voltage, don't have enough energy to get across that barrier and they get turned away. So now I'm completely dominated by diffusion current. And we've talked about all these ideas. I get the, do I have the, yes, okay, well, that time. This is the voltage versus current versus voltage plot for a diode. It's modeled by that ideal diode equation. There is one additional region I would like to talk about because I know you don't see it. And it's amazingly useful. Have you, anyone in here ever heard of a Zener diode? Okay, you've heard of a voltage regulator. Okay, so a Zener diode is the start of a voltage regulator. It turns out there's a voltage here, and unfortunately, oh great. Oh, I know what, I know, I can fix this one. Okay. I'm in between slides. Right here. There's a voltage right about here that they call the breakdown voltage. And they called it that, and it's a bad name because it doesn't involve breaking, and it's not a bad thing. It's actually also called V-Zener, named after the guy who discovered this. If you put the diode too far in reverse bias, it starts to conduct again. It's avalanche multiplication of carriers. They have so much energy, they can get over that bigger barrier. And this looks like, if you look at this, I is fairly constant and V changes. So this looks like a current source. I know it looks like a voltage source. Sorry, I said that. I'm thinking backwards. This looks like a voltage source. It's a constant voltage around about the value of V breakdown. I can put as much current as I want to through it, and I get a constant voltage out. This is the start of how people build those voltage regulators, linear voltage regulators. They use a Zener diode, which isn't perfect. It doesn't have great output impedance. And then they put a big amplifier around it, and they put an amplifier on the end. They put some stabilizing circuitry in there, and then you have a good linear regulator. So that region does exist, and it doesn't involve breaking the diodes. There's no smoke involved. It's non-catastrophic as long as you don't get the voltage too high. I don't want to talk about this. This isn't very useful at this point. This is I definitely need to talk about. And we're almost done. This is the last slide. SPICE. It is multi-sim that you've been using. And also Metagraphics, which we'll use in 380, when they look at diodes or transistors or things like this, they're inherently nonlinear devices. But computers aren't good at handling nonlinear equations. They're much better at handling linear equations. Capacitors have a negative current in their neutral state. Capacitors have zero DC current when they're acting really like capacitors. It's like a capacitor. The capacitor is part of the model, but there's ideal capacitors have no current, DC current flowing through them, only AC. The way you get around this, and I was doing this summer, I was modeling a device that looked like a capacitor, but we were able to inject small DC currents through it. And the only way I could model that as a linear model is I took a capacitor and I put a resistor in parallel with it, a really big resistor in parallel with it. And then I could get my 100 nanoamps through there and have a semi-ideal model, and created a linear model of a ReRAM cell, and then used it to bop an ASU professor on the head. I did it good. He annoyed me. He made fun of my lab kids. He was bullying my lab kids, so I had to bop him on the head. Okay, that's my job. Oh good, now I can draw. This was the model I came up with for the device. And he was telling us that the capacitance was dominating. And I calculated the capacitance and I calculated the resistance and I did the differential equations and did the Laplace transform of it and all that stuff. And I came up with an equation at the end and go, look how we're measuring it. The capacitance only affects our measurement if it's like 1,000 times bigger than what it actually is. So we're not in trouble. The capacitance doesn't matter. And he's been yelling for 2 years that we don't know how to make the measurement because it's all capacitance. Okay. So what this idea here, when we're looking at the device, is we do the same thing with diodes. We want to create a model of the diode that looks like a linear circuit. It has inductor, no, it doesn't have inductors in it. It has capacitors, resistors, dependent voltage sources, possibly dependent current sources in it. And we create this linear model of the diode that approximates its nonlinear behavior. And what they do is they take this and they put it all in this model file that it gets attached to the diode. And so every time they model the diode, it will be based upon this. You can change the parameters for different diodes. Multisim is great. They go out for every manufacturer, even up to like ICs, op amps, things like that. They go in and they create these model files for you. And if you attach those model files to the picture, it will simulate it correctly. You'll get to mess around with one of the model files in lab 6. This is a 1N914 diode. Weird things about, and this is stuff about the package, the type it is. This is the heart of the model right here. It gives you IS. They don't include units. This is a SPICE standard thing. When they talk about IS, you got to know it's a current, and the default unit is going to be amps. So that's why everything's 10 to the minus 9. Capacitors, farads. Resistors, ohms. They put a resistor in this model too, and that resistor has a value of 0.78 ohms. There's some multiplication factors. Transit time accounts for delay. That would be in seconds. The capacitance of the diode at 0 bias. And then it models the diode based upon these curves. Puts it into a linear model. All simulators have this in it, whether you see it or not is another thing. Multisim is great because you can go out and pick up a 741 op amp and put it down on your schematic, and it already has the model included for it. If you are using a more exotic, one of the newer op amps, Multisim may not have that device in their library, but there are people like Ultra Librarian that will create multi-sim models for you, and you can download them. You can download the software for free and actually download the models through DigiKey, through people who are selling you the parts. So they want to help you succeed. Don't ever try to write this on your own unless you're the guy building the new op amp and you have to make the model and make it work. Use other people's work. There's a lot of things that's like GitHub, but it's for electrical engineers. And there's like Ultra Librarian is like kind of like one of those GitHubs, but it's standardized and it's traceable back to the manufacturer, so you know you're getting a good model. Because if your model's wrong, your whole thing doesn't work. Okay, good. Any questions? We got 5 minutes, or we can go. A lot of stuff covered in 1 week, but at least it wasn't all mathy. The homework is mostly just calculations, making sure, just going through and checking. The most difficult part about it is making sure you put everything in centimeters and then plugging in the numbers and then calculating it right. Okay. Pseudo spring break next week, no labs, no homework due in this class, and no pre-lectures. So get caught up on everything else. Maybe finish up lab 4 if you need to, and we'll start lab 5 afterwards. Lab 5 is less mathy, more circuits. Okay. All right. Oh, who's not here? Ibrahim. Austin.
Yes, Austin is here.
Yay. Zach Schreiner and Mark. Everybody else is marked here.
Zach Schreiner's here.
Zach Schreiner, you are here. So now we're down to Ibrahim and Mark. Good. All right, we'll see you guys. Oh, good, there's chat stuff. Is there a class? Basic, okay. Jordan, I teach a class. It's my 490 in the spring. It is on memories. It's a system level look at the first half of the class is a system level look at a DRAM chip, where we look at all the various pieces that and how you read and write out. It's the closest thing we have to an ASIC class. It includes a lot of the CMOS circuits. Oh, the CMOS circuits we do a lot in 380 too. We cover most of the logic that 380 is required. 490 goes a little bit deeper, where we start looking at the way things actually get built inside an integrated circuit. And we talk about signal, we talk about all the stuff that goes on inside an integrated circuit. I took quantum physics. When I first graduated, I took a whole year of quantum physics in the physics department. When I first graduated, I applied for a job as a test engineer and they laughed at me. It has been amazingly useful in my life though, because when I started dealing with electro-optics, different types of conversions through there, I have applied it, and I'm about ready to build a big quantum key distribution system. So yes, the quantum physics for engineers is good. There's also a quantum physics class over here in the physics department, and I think the prerequisite is modern physics. If you're a physics minor, it would be useful, and it would relate back to electrical engineering. And the biggest thing too is the device dimensions keep getting smaller and smaller. We get down to the nanometer scale. These quantum effects inside transistors are getting to be more important. So understanding them as you're going through the design process is getting to be more important too. Yeah, modern physics. What was modern physics? It was relativity, Feynman's KQD, quantum electrodynamics, a little bit of that. Things that I'm talking about with solar cells, where the photon comes in and excites an electron, that gets included into modern physics, Planck's constant, a little bit of electro-optics and stuff like that. Yeah, I would definitely find that to be a useful class. Okay, and I'll see you guys pizza night with no pizza.